In example 12.10, we have a word problem. And the part that I want to focus on at the beginning is the part where the narrative is located. That's going to be all of this right here. Now, the key to working with these word problems is recognizing the equation that's provided and then understanding what variables are being represented within the equation. If you understand what language the variables represent, then you have a chance at being able to answer the question. Otherwise, that equation becomes basically worthless and you're just guessing at what you think you're supposed to do. So let's read from the top. A ball is thrown upward and outward from a height of 6 feet. Perhaps you have a fond memory of, as a child, throwing something maybe across the room, parents yelling at you, don't throw in the house, blah, blah, blah. I remember doing that with my brother, constantly trying to throw things and make them into laundry baskets from across the room. So essentially what's happening is we have, starting at 6 feet, somebody throws the ball upward and outward, and then eventually it'll come back down. So whether you've known this or not, the path of the ball as it's being thrown is a parabolic path, which means that there is a maximum point at which it reaches. Now, the way that I've drawn this would be based off of my own intuitive understanding of my own experiences of throwing a ball upward and outward. It would be consistent with the equation that follows. It says the height of the ball, and then it has comma f of x separated. So this tells me what f of x is supposed to represent. Remember, f of x basically is the y value. So on my my little graph here, that would mean that this is height on the y-axis, and it says that the height can be modeled by the equation, and then here's the equation. And notice that in this equation, the a value is negative. Since a is negative, that means the parabola should open down, which is precisely what we drew. Now with the rest of the narrative, it says where x is the ball's horizontal distance in feet. And I guess I may have stopped a little short up here. After f of x, it also says in feet. So we get the units as well for what we're dealing with. So that means along the horizontal axis, we have horizontal distance. Horizontal distance. And this is x and f of x. So now that we understand what the narrative is describing and what the variables represent in the equation, this would give us a chance to actually be able to do something correct with the equation. Part A, here's the question. What is the maximum height of the ball? And how far from where it was thrown does this occur? There's only one place in this picture where we have a maximum, and that's going to be at your vertex, located at h, k. Now we know that the height of the ball is represented by the y value. So when it says maximum height, it's referring to the value of k. How far from where it was thrown does this occur is a little bit vaguer than the first portion of the question, because it just comes right out and says maximum height. This part is actually referring to horizontal distance. So k is represented by this vertical distance here, and h is represented by that horizontal distance there. So if you go right and then up, h and k, that's how you'll get to the vertex. So essentially what part A is asking for is the different components of the vertex. So we'll do that calculation. For part A, we'll calculate h using our negative b over 2a formula. We go up here and mark where b is. B is 2.4, and then c is 6. So this will be negative 2.4 divided by 2 times negative 0.8. And with the arithmetic on that, you should eventually get 1.5 feet. For K, K will be calculated as f of h, or f of 1.5. So we'll plug that in, negative 0.8 times 1.5 squared plus 2.4 times 1.5 plus 6. And this is where you would definitely want to use a calculator. Since the answers are all given in decimal, it'll be fine to get a decimal approximation if necessary. Now it turns out this answer ends up being exactly 7.8 feet. So we have the value of K, the value of H, which represents the height and the horizontal distance that is associated with the vertex, or the maximum. So then we just write a little something sentence-wise that would answer the question. Here's an example of what that might look like. Say the ball reaches a maximum height of 7.8 feet at 1.5 feet from where it was thrown. Lots of ways that you can state this information, 7.8 feet, 1.5 feet, with regards to the question, but I don't need a full page or even a full paragraph. One sentence or maybe two sentences, if you want to break it up into two, works just fine for me. Let's move on to part B. Part B says, how far does the ball travel horizontally before hitting the ground? So if we're talking about the ball traveling horizontally, it starts horizontally from here and eventually gets all the way to the ground over here. So what I'm looking at calculating is an X-intercept. So to calculate the X-intercept, regardless of what type of function it is, you are always going to let the equation be equal to 0. When we do that, we will then have the statement 0 equals negative 0.8x squared plus 2.4x plus 6. And this is where I would be interested in applying the quadratic formula. The quadratic formula, I'll write it down, x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. This would definitely be one way of doing this. Another way of doing this that we saw earlier in the section would be to take the equation and write it in its vertex form. That would certainly be one way that we could do this because we have the vertex already. Since we've already done that once, let's use the quadratic formula instead. So substituting in, we're going to have negative 2.4 plus or minus the square root of 2.4 squared minus 4 times negative 0.8 times 6, all divided by 2 times negative 0.8. The first place that you'll want to simplify is the portion underneath the radical. So follow the arithmetic, and if you do that correctly, you should get approximately, or it'll be exactly 24.96. And all divided by negative 1.6 there. Now at this point, nothing's been approximated. Everything is actually exact. But when I take the square root of 24.96, which is the next thing I want to do, I'm going to get a nice long decimal that I'm going to have to round, which means I'm now going to have an approximation. So in order to represent that approximation, I just use the approximate symbol, approximately equal, and it's going to be approximately equal to 5 divided by negative 1.6 there. So what we get is two different answers. We get potentially negative 1.6 and positive 4.6. The negative answer would imply that the ball was going behind us. But the narrative very clearly says the ball is thrown upward and outward, not behind us. So this answer doesn't really make a whole lot of sense, although it is technically there. If I go back up to the picture, you can see that if I was to take where the starting point was and go backwards with the parabola, it would eventually cross the x-axis over on the negative x values. So it's up to us to understand what portion of the parabola we actually want to use, because we don't need the entire parabola to model this particular event. So going back, we know that 4.6 makes far more sense than what we originally, than the negative 1.6. So we'll make a little sentence. The ball travels approximately 4.6 feet horizontally before hitting the ground.